Again, welcome to Data Structure and Algorithm. This is CS435 class. In this lectures, we're going to cover the concept of queue data structure. So our main objective is to learn about queues. We're also going to examine various queue operations. And also we're going to learn how to implement a queue as an array and also as a linked list. We're also going to discover queue applications. So what is a queue? An example is given here. For example, if we go to a bookstore and we have a couple of things in this picture here, we have 4 people. The first person in the queue will be served first before the next person. Now, if a new customer comes, it will join the queue from the rear. So the rear of the queue is where we insert an item. The front of the queue is where we remove an item. So unlike data structure stack have only the top of the stack. We can set an item or push an item through the top of the stack. We can only remove an item also from the top of the stack. So the entry and exit to a stack is only one place. Unlike a queue, we have the entry different location. Exit of the queue also is different location. So the front of the queue will be the exit, and the rear of the queue will be the entry point to the queue. So this means if we are going to implement a queue, we may need the 2 variables to keep track of what is in the front and also what is in the back of the queue. So here we say a data structure in which elements are added to the rear and also removed from the front, which is first in, first out structure. So using queues, there are few examples given here. So the major example is operating system. So operating system often maintain a queue of processes that are ready to execute or that are waiting for a particular event to occur. So in the concept of operating system, multi-processing system, we may have more than one process that need to be executed. Operating system also can use the concept of priority queue. So a process may be executed based on its priority. And so it's very common in operating system implementation. Also, the same thing applies to networking system. When we send a job to the printer, the first job that arrives first will be printed first. So the concept of, again, queue, first in, first out. So here also we say computer system must often provide the holding area for messages between 2 processes or 2 programs or even 2 systems. This holding area is usually called a buffer and is often implemented as a queue also, because the first item that comes to the buffer will be the first item to be coming out of the buffer, first in, first out. Also, our software queues have counterparts in the real world queues. Example here is when you join a queue to buy a pizza, most likely you have to join from the rear, unless you have some criteria, some priority. So we also have a priority queue, which means you'll be served first based on some criteria. Same thing applies to enter a movie theater. Maybe the president of United States may not join the queue to enter a movie theater. Again, that's a priority queue. So data structure in which the elements are added at one end called the rear. So data are added at the rear of the queue. And also data deleted from the other end called the front of the queue. So again, the queue is a first in, first out data structure. As in stack, the middle element of the queue are not accessible or inaccessible. So we can't remove any item from the middle of the queue. We remove from the front of the queue, we insert from the back. In stack, we remove and insert from the top of the stack. So these are some of the queue operations. We can initialize a queue. We can also check if queue is empty. We can also check if queue is full. Again, this is if it's an array implementation. We can check it by the size. Now here we have two more operations here. Front, we check what is in front of the queue. And back, we check what is in the back of the queue. And also addQueue, we can add elements to the queue through the array of the queue. DeleteQueue means we remove item from the queue from the front. So this means if we are adding a queue, we're going to increment the back. And also if we are removing item from the queue, we are going to work with the front. So adding an element to a full queue and removing an element from an empty queue will generate errors. Same concept as a stack. So we also have a queue overflow exception and also queue underflow exception. And this is a built-in runtime exception. Again, we are using Java here. So we start with the implementation of queue as an array. As we said earlier, again, array has a face size. Unlike linked list, which is dynamic, array is static, face size. So first, in the queue, the same as in the stack, we have to declare our array and also specify the size of the array. So we also have a queue front. This will be a variable that will keep track of the first element in the queue. And also we have queue rear, which will keep track of the last element. So again, in stack, the instant variable was only the stack top. Here we have the queue front and also the queue rear. The max queue size, just the size of the array, represented by max queue size variable. And of course, we have to also declare the array. So this is an example of a queue after we perform two hard queue operations. So this is an array implementation. The size is 100 because the index starts from 0 to 99. And we did queue front. So we have items, front will be A, and also queue rear, it will be 2. So again, we have 3 elements in the queue. The front is 0, second B, the rear is C. So this means these two variables normally will indicate the index position. Queue front, the beginning, queue rear is the end of the items. Now, if we perform a delete queue operation, then we are going to again remove from the rear. And we're going to implement again the array implementation. Now, the problem with the array implementation, let's go back to the diagram. If we insert an item and remove, insert and remove, what will happen is that we normally will insert through the rear, but we remove from the front. So let's say we insert an element up to 97, and we remove like 96 of the items. But our last element is still 97. When we insert 2 more items, it will be 98, 99, which means we cannot insert no more items because we end at 99. But we have empty space from 0 to 96. We have only 4 elements, 3 elements inside the array, which the size is 99. But because of inserting, deleting, inserting, all the front. So this problem will be solved by using what we call the circular array, which means I will let the last index here start point to 0 or start to 0. So it will be like a circle, and we will see that in a second. So problem with this implementation is that array have a face size. After various insertion and deletion operation, the queue rear will point to the last array position, giving the impression that the queue is full. But again, we have elements in the front. So what is the solution? we're going to slide all of the queue element toward the first array position using the concept of circular array. So this is how it will look. So even we reach 99, next time we can put an item, the rear becomes 0. Front is 99. There, we keep going. So queue with 2 elements at position 98 and 99, which is X and Y. Then next time, if we do hard queue operation, the item will be at Z. So again, Z is not our front. Even the index is 0, is the rear. This is again circular array. So our front is X, 98. So we can see here queue front is 98. Then the queue rear is still 0 now. So let's go through the code. So here we have the default constructor. We say the array size should be 100. So the mass queue size, we assign it to 100. Make sure the queue front is 0. So we don't have anything. And also the queue rear will be the mass queue size minus 1. And so from 0 to 99. Now we have a special variable called count. This will tell us how many elements we have in the queue. So anytime we add an item to the queue, we increment the count by 1. Anytime we remove item from the queue, we decrement the count variable by 1. So here we create our array name is list, data type is generic T, and the size is the mass queue size, which is 100. So again, this is our default constructor to, again, create a queue class object, empty. The count is 0, which means we don't have anything. Also, to initialize the queue, for example, we use the queue a couple of times, and now we want to delete everything from the queue. Same concept as stack. So here, we are going to start from the queue front. Now, the queue front can be 0, it can be anywhere. Here, remember, we are using circular array. So that's why we said I is less than queue rear. So it will go up to, if the size is 100, to go up to 99. But instead of saying I equal to I plus 1, which is to increment, anytime we want to go through an item in an array, we increment the index by 1, moving from first step to second step, moving step by step. Here, it will not work that way. So you can see that we say I equal to I plus 1. What will happen is that if we are somewhere, let's say we are 96, perfect. If I say I equal to I plus 1 and I is 96, then we get to 97. 97 modulus 100 will still give me 97. So I'm good. Now, when we reach 98, okay, 98 plus 1 is 99. 99 modulus 100 is still good. We are 9. But now, when we reach 99 and we are moving to 100, now when we had 99 plus 1, 99 plus 1, yes, modulus 100, we get 100 modulus 100, which will give us 0. So this means we are telling the index to move to 0. So this line here make it possible for the circular array. Now, if it's a regular array, we say I equal to I plus 1. When this condition become true, I is less than Q rear, which is, let's say, go to up to 99. When we plus 1, we go 100. 100 is less, so we stop. By here, when we reach 100, 100 modulus 100 is 0. So now I is 0. Is 0 less than Q rear? Yes. Then we give circular array. So this for loop will make possible for us to go through the items in the queue. Now, when we go through the items in the queue, we want to initialize it. So every item, we are going to assign null to it. And this will make it possible to initialize all the items in the array to null. Then we set the queue front to 0. And also we set the queue rear to mass queue minus 1. And also make sure the count variable is 1. So initializeQueue will make sure our queue will be in a state of emptiness, empty state. There will be no any item inside. Also, the same thing, we can check if the queue is empty. Remember, we are using the variable count. This is the reason why we are using variable count, because with a stack, the entrance and exit is a stack top. So we use the stack top to know if there's how many elements we have, etc. But here, since we have a queue front and queue rear, we can't use any of the two. Any of the two can't tell us how many items we have in the queue, because different entrance. So this is why we are using special variable named count. Anytime as we increment or insert an item into the queue, we increment the counter. If we remove item from the queue, we decrement the counter. So we check if the counter equal to 0. If it's equal to 0, that means the queue is empty. And now this is a re-implementation. So we will also check if the count equal to the mass queue size. If the size is 100, the count is 100, that means the array no more size is full. There's no more items, location to put an item. It's full. So we also have a method front. This will tell us what items in the front of the queue. So of course, if I want to check if there's anything in front of the queue, first of all, we don't want to check an empty queue. This is a re-implementation. So first we call the method is empty queue to check if the queue is empty. If it's empty, then we throw the queue under for exception. If it's not empty, then we'll return the queue front. Remember, we said the instant variable queue front and queue rear tell us the positions of the first item and the last item, but it doesn't tell us how many items we have in the queue. So this is queue front, return the array name is list, data type is generic T. So the same thing with the back, we return the queue rear to check what is in the back. Same thing, we also have to make sure the queue is not empty, so we check if it's empty queue. If this is true, then we throw queue under flow exception. If it's false, then it works. So next is to add an item to the queue. So we use the method name addQueue. Again, the method can be any name, and different textbooks use different name. So this is to add queue. It takes one argument, the item or the element we want to add. And here we want to throw, again, this is a re-implementation. So throw queue overflow exception, because we're going to check if the array or the queue is full. If it's full, then we throw the queue overflow exception. If it's not, then we are going to, again, add an item to the rear of the queue. So we have to increment the rear by. Now here we don't say, if we say queue rear equal to queue rear plus 1, it means again, we have our regular array. But here circular array, so we say modulus mass queue size. So that when we reach the last index, 99, we go back to 0. So after we increment our queue rear, then we're going to assign the item to it. So we increment the counter, of course, because this counter again, just to tell us how many items we have in the queue. Then we assign the queue element to the array queue rear. So the item will be at the rear of the queue. That's what first thing we do, we increment the rear, the queue rear, which is queue rear plus 1 modulus mass queue size circular array. After we increment it, then we assign the element to it. So the count, we can either increment the count variable before we assign the element to it, or we can assign the element to it after we increment, after we assign. I mean, here we wrote count plus increment the count variable, then we assign the element to the queue rear. or we can assign the element to the queue before we increment the counter. It's all the same. The main process is to add a queue array implementation. First, check if there's a space. If there's a space, increment the queue array and assign the element to it. Then we can increment the count variable just to keep count of items we have in the queue. Now, to delete item from the queue, we have to deal with the queue front. So first of all, we don't want to delete empty queue. So we check if the queue is empty. If it's empty, then we throw the queue underflow exception. If it's not empty, then we decrement the counter. Remember, we are reducing the item by 1, removing an item. So when we decrement the counter, we assign no to the queue front. Then when we assign no to the queue front, we move 1 forward. So queue front plus again circular queue. So we use queue front to be equal to queue front plus 1 modulus max queue size. So the main code is 2 sections. Assign no to the queue front and then move queue front 1 step. So next is the link implementation of queues. Again, same concept. The only difference, as we said, link is a dynamic implementation. And also linked list consists of nodes. So that's where we have to pay attention to. So let's look at the code. Or the operations, the theory is the same as array. So first we want to initialize the queue. Here we are using linked list. The linked list consists of nodes. When the nodes point to the first special node point to null, it means there's nothing there. Linked list. Here we have 2 pointers now. 1 for the front, 1 for the rear. So if both queue front and queue rear are known, it means there's nothing. The next is to check if the queue is empty. So we have to make sure the queue front is equal to null if it's empty. Also, we want to check if the queue is full. Again, this is dynamic implementation, so it will always return false. Then next, we are going to add item to the queue. Same concept as stack linked list implementation or link implementation. We need to create our node. This is dynamic implementation, so we need to create our node using the new keyword, which dynamically allocates memory space. We also need a constructor for the node, queue node. So we have a queue node class, and we call the constructor of it to create a new node object, type queue node. So next we said that if the queue front equal to null, which means initially we want to insert an item to a queue, initially the queue is empty. Well, if the queue is empty, then the first node that we are adding, it will be the queue front. We assign the new node to the queue front, and we assign the new node to the queue rear because it's empty. But if it's not empty else, then we need to assign the new node. Remember, we insert an item to a queue from the rear. So we move the queue rear dot link. We move the rear 1 step. So we can get space and put the new node there. So after we put a new node in queue_rear.link, we increment the queue rear by saying queue_rear.link assigned to queue rear. So next is to check what is in the front and back. Our method front checks what item is in the front of the queue. So we check if the queue is empty. If it's empty, we throw queue underflow exception. If it's not empty, then we just get the queue front.info. Remember that we have the node consists of info and a link. It can be any name, but info here means where we store the data. Link is the address of the next node. So if I return queue front.info, queue front is pointing to the first item, the first item in the link list. In this queue link list. Same thing if I'm doing the back, I'm going to use the QRare. So I need a QRare.info, return the QRare.info. Also, we have a method to delete queue. So if you want to delete queue, again, the same concept as you said, I want to delete an item from the queue. So first of all, I'll check if the queue is empty. If it's empty, I'll throw the queue under full exception. Other than that, how do we delete? We delete from the front, or we move out of the queue from the front. So we move the front forward, queueFront.link assigned to queueFront. So we advance the queueFront. Then when we advance it, we set the previous queueFront to null, make sure there's no value there. This is to delete the item. Then we set the null also to the QRare. If it's empty, set the QRare also to null. Because here we are saying that if queueFront equal to null, then QRare also should be null, which means it's empty. If this is false, then the only thing we did is to advance the queueFront .link, which means advance the queueFront one step. But if there's nothing inside, if the queueFront, we advance the queueFront one step, and later the queueFront was null, which means it was one item which we delete. So this means we're going to set the array also to null, which is null assigned to QRare. So we have so many applications of queues, as we saw previous example. Operating system use it, computer networking use it. Operating system use it a lot for multi-processing or multi-program, multi-threading, because in this case, a multi-process means we have more than one process to be executed, but they have to wait. So they can wait in a special queue, which we call the buffer. First in the buffer will be the first out. So it's first in, first out. Also, here example is simulation. This is a technique which one system models the behavior of another system. It can be used when it's too expensive or dangerous to experiment a real system. So we can also design computer model to study the behavior of the real system. Queuing system, and that's a queue of objects are waiting to be served. So again, that should be the end of our lectures, and we have the lab work to be done. Hopefully we do the lab work in class. Also assign the homework, which we are going to implement. Again, the code, the queue operations. We are not going to use the Java library file or package. We are going to use the code, our own code for the lab work. So again, wish everybody the best. Thank you for your time.